So hello everyone. Today we're going to talk about the binary search tree. Before we start talking about binary search tree, as you can see, we never talk about tree structure. So even from its name, you can tell that we're dealing with tree. So I have to define the tree. We're not only dealing with tree, but dealing with a binary type of tree. So we need to define what is a binary tree is. And then more specifically today, we're going to just cover specifically binary search tree, which is another specific types of binary trees. So let's just define what is a tree structure. So far, whatever the structure that we saw, all the list of structures that we saw that helps us to store data, were linear, right? So we didn't have any type of a structure so far that we can represent them with a some sort of a hierarchical way to represent the data. And so tree structure is a way to presenting the type of a data that naturally also they have this hierarchical order between themselves. So, you may call them tree, but you may want to think, okay, the way that we draw them. So this is how we draw a tree structure. You might want to think that, okay, the way that we draw these types of tree, they not really look like a real tree that we know normally. And so, okay, so let me see what happened to my, if you can see it, okay, perfect. So this is how we're showing the tree. So if you really think about the tree that we have the actual representation of a tree, it's going to be completely opposite. So, but here we basically kind of think about as the root of the tree, or whatever is considered as the roots on the top, and all the leaves are going to be on the bottom. So it's going to be opposite of the actual tree structure. This type of structures are usually conceptual. So in they have different use in different fields. We have the tree and data structure, which we're mainly using it in computer science, but we also have a huge graph theory and tree or set theory that is going to be related to that to the same concepts as well. So the basically computer science, when we're talking about the tree, we're mainly talking about the basically abstract data type that we're trying to represent or simulate data structures that look like a tree. And roots usually is going to be the starting point of it. And it has a value, and then we have a bunch of subtrees, and the subtrees are going to be the childrens of the root. So the tree, basically only going to have one root, and the childrens of the tree, each one of the roots, each one of them, they can create their own subtrees, and they become the parents of their own nodes, right? So basically, each subtree also going to have its own root, and therefore they're going to have their own set of children. So basically, root is going to be the parent of all the other children, and as we go recursively to every other levels of our tree, you can see that each subtree also itself is going to have a node as a root. So we are storing the data in those basically or the values that we're trying to store. We store them inside the node, and so each node is going to know who's the father, who is their children, and and what is the value we're storing in it. So another thing about the tree is that each tree, sorry, doesn't need to know about their parent. They know about their children's only, right? So they don't need to know about their father. Just want to clarify that as well. So you see the picture of it on the board, right? So we have the root and we have all the children's that, you know, the children's also have their own children. So they're creating different subtree. So we're kind of consider this as an ordered tree, and so we're trying to kind of put this as we adding. So this is a data structure, right? So we inserting data into it, we're removing data from it. We like to search in it and find a particular data that we store because we're using it for storage, and so we need to have mechanism to add it and delete it and and search on it. So or even like in a very particular order, we go through the different nodes in this tree. So basically, one of the definitions that we have is the nodes, right? So each tree is going to have at least one node, which is the root, and the root doesn't have any parents, so that's going to be the only basically root. That's why we know it doesn't have any parent. That's the one that doesn't have any parent, but it may have some children. So how we connect the children also themselves are going to be nodes. So how we connect these nodes together, we call it edge, right? So each basically tree is going to have a set of nodes and a set of edges. So that you can see later on, we're going to talk about graphs, and graphs also, then you have the same exact concepts. The graph is a set of nodes and set of edges that they're connected to each other. But the way that we connect trees, so basically we say tree is a specific type of a graph that we do have a root. We're starting from the root. Root doesn't have any father. And then from the root, we go to different subtrees of basically our tree. Inside our tree data structure, since also we call them like hierarchical data structure or non-linear data structure. Inside it, again, like what we have in any list or anything, right? If you don't have anything, that means you don't have any nodes at all, right? So there's nothing in it. And immediately when we're adding at least one element, that element is going to be the only element if it's only element in the list, and that's going to be our root. And then if you add more, then root's going to have 0 or more subtrees. Basically from there we're going to go to its children, and children is going to have their own children, so they're creating subtrees. So definitely we need to have a basically root doesn't have any parent, and also we don't want to have cycle. So the tree structure doesn't have any cycle in it, so we cannot go to a node and then come back to the same node again as we visit the nodes through the different edges, right? So if we keep going from one node to another through the edges, we should not be able to get back to the same node again, because if you do that, that means you do have a cycle in your tree. So the tree doesn't have any cycle. So if, immediately when we find a cycle, we know that's not a tree. There are specific basic definition, as I said, about the tree that make it different from the graph itself, right? So and also as far as the directions, you can have a directed tree as well, but we always know that we're starting from the root, and then from the root we go to other children. So even if you start, the direction is going to start from the each parents are going to point to their own children if you have a directed tree. We have also other concepts in basically in the tree, and that is, for example, the levels, right? So what is a level meaning in a tree? So as we're going through from the root, we start going to the very first children, and we connect those using, as I said, the edge. So each node, but when it is a root, We know it's a root, first of all, because we, as I said, it's not going to have any parent, any other parents, but it's going to have some children's, and the children's are going to be directly be connected to the node. So those are the children's of the roots, right? So immediately going to be connected. And the siblings, they have the same father, right? So they have the same parent. So all the immediate nodes right after the all the immediate nodes right after the roots. There, here we have the root as 60, for example, in the picture A, and the children's of that are going to be 55 and 100, the values of them, so because they're connected through an edge directly to the root. And then they also are siblings. So siblings are going to have the same father. So here also F and R, they both have the same father, G, and the G is the root, and so they're also considered sibling. So the neighbors are having the relation of a parent or child relation. So that's how we call them neighbors. So basically you can connect them through either, you go to them through either one edge. So that's how we basically consider them as neighbors. So that's another definition. Leaf are the basically the nodes without any children. So here in the picture A, 45, 57, they are siblings because they have the same father, and they are leaf because they do not have any other children. So they basically become leaf. And here also A, M, and T, they are leaf as well. M and T are siblings. A is not the sibling of M and T because they don't have the same father. The father of A is F, and the father of M and T are R. So they're not siblings. But what things you can see when you draw this in a kind of nice order from the roots, you can see that A, M, and T in the tree in the picture B, they are in the same level. And that means that if I consider the root as level 0, if I go one edge, then I find one edge to the left, for example, or one edge to the right, I find all the nodes in the very first level. And from there, if I go to another path or another edge, then I can find all the other nodes that are in the same level. So the levels are basically number of edges that we have to count from the root. So from G, if I want to go to A, I need to go through 2 edges. So A is inside the level 2. Same thing, if I want to go to T from the root, I have to go through 2 edges. First, I have to go to R, so I pass one edge, and I from R, I have to go to T, so I have to pass the RT edge. So I have 2 edges. So that means that they're both going to have their basically they're on the level of 2. When we're counting the number of edges, we call it length. So the length of T is 2, the length of R is 1 because I just have to go through one edge to get to the R from the root. So basically another way to say that the nodes that are in the same level, they're going to have the same length, right? So the length F is 1, the length of A is 2, the length of M is 2. So the number of edges from G to M. And also from G to M, I do have 2 edges. So the length is 2. Also, that's a path that I have to go, right? If I want to go from G to M, the only path I have is going to R, and then from R, I can go to M. And that's considered a path. That's basically path.